We got this roof truss, and we like to size it, size the member. What size should we use for the amount of loading that we have? The roof is about 30 feet apart. I mean, you can go to Home Depot and other places to buy pre-made truss, but sometimes you might end up with the width of your room. It might not be standard, it might be different. So you can make your own. If you want to make your own, this is one way you can do that. And this truss we're going to build, we're going to be on 4 feet on center. I mean, every 4 feet you're going to put one truss, every 4 feet you're going to put the other truss, and you're going to put the roof over it, plywood. The load is, you can go to the code, depending where you are, based on the code. Say we got 30 pound per square foot of snow. Around here probably it's more than that. And then you got dead load, which is the weight of the material itself. It's going to be 14 pound per square foot. We're not going to count for roof life load, but we can add 20 pound per square foot of roof life load, say if somebody going up there. But for this example, we're not going to put it in there. Then this roof also, down bottom, you have the ceiling hanging off the truss. You know, you're going to have sheetrock or whatever you're going to have, or board. You're going to have bottom of your truss. Just what I have, like those pictures you see. And that comes out to, I already converted that to 32 pound per foot. Let's go ahead and convert this pound per foot, because this is given by pound per square foot. And also what it tells you that every 4 feet, I mean your turbo tree width is 4 feet. So our total load in here is going to be 44 pound. And then if I multiply that by 4 feet, and that should give me a pound per foot, which comes out to 176 pound per foot. So this number right here comes out to 176 pound per foot. And down here we're all set. Next thing I want to find out, say this truss is basically simply supported. That means it's hinged on one side and make it simply supported. So we want to find the reaction, how much reaction forces you have on both sides for support. And if you look at any beam formula book, basically this is based on this uniform distributed load for the top. So this reaction, we're going to call it reaction force of the both right and left are equal, and that is equal WL divided by 2, which is equal, so W for this one is 176 times 30 feet divided by 2, plus W for this one is 32 pound per foot divided by 2, and no, I lied. I'm going to multiply by 30 here. Multiply by 30, then that is equal. That's 3120 or 3.12 kip. So this is going to be right here, 3.12 kip or 3,120 pound. Same thing here, 3.12 kip. Because this is a truss, I want to go ahead and simplify it and analyze it. Truss, one thing you need about it is they have a joint. Joint here, joint here, joint here, joint here, and a joint down here. That's where they connect. So all load are applied at the joint. So I got to take this load, make it a joint load, make it a load here, load here, load here, here, and here, and then take this one, make it here, here, and here. So let's go ahead and do that. First we're going to deal with the top, which is 176 pound per foot. And it says right here, for each bay, this is a 4 bay. 1 bay, 2 bay, 3 bay, 4 bay, and each bay is a 7.5. So if I go ahead and make a line here, that's 7.5, that's a 7.5, and that's a 7.5. 176 pound per foot time 7.5 feet. So feet cancel each other out. That comes out to 1,320 pound per joint. So I'm going to come in here. I'm going to say, okay, right here per one joint is right there, 1,320. Since this is a kip, I'm going to put this one in kip to 1.32. Now here, you gotta remember, it's not 1.32 because it doesn't get the full. When you look at this joint, let's look at that joint right there. That joint right there has a force of this on top of it, and this is gonna be 7.5 feet. But in here, this one only get half of a 7.5 feet, so it's gonna get half of a 1.32, which that become 0.66. So that is a 0.66 kip. That's half of that. And this one will get a, let me put this in different color. It's 1.32 and 1.32. Right here also we have 1.32, and the pitch of the roof is 6 on 12. And this one is going to be a 0.66 kip. And now we're going to come back in here. We're going to take care of this one. This one is only have the 3 joints, so each joint is about 15 feet apart. So therefore, we're going to say, okay, for that one, it's going to be 32 pound per foot times 15 feet, because the distance between each joint is 15 for the bottom. But on top, the distance are here to here is 7.5, here to here is 7.5, and so on and so forth. And this is going to come out to 480 pound per joint, or 0.48 kip per joint. So in the middle right here, for this truss, I'm going to have 0.48 kip. For here and here, it's going to be half of them. It's going to be 0.24. So I'm going to put that in a different color. Let's say that is a, for this one is a 0.24, and one over here is 0.24. Basically what I have done here so far, I'm going to say, okay, I took this load. You cannot use it because truss, the load is on a joint. So you got to convert this load per each joint. This is a 7.5 feet, so multiply that by 7.5 feet, and that's why they came up to it. This is a 7.5 feet, but it's only going to carry half of it. That's why it became 0.66. So we did all 4 joints on top. And we took this one on the bottom, 32 pound per foot, and we made that per all 3 joints, and that's what the number came out to. Now we have that number. We can go ahead, figure out, you done this in the kindergarten, we're going to find out what is each member, how much tension or how much compression has. In truss, normally the bottom chord is in tension, the top chord is in compression. When you look at this, you got a load on top of this truss here. And this truss, what is that doing? When you have the load on, it's going to pushing out, and therefore this member is holding it back. Otherwise, it's going to collapse. So it's holding it back, it's in tension. And that's how it goes. So let's go ahead and let's get to work. So now we're going to come in and isolate this joint right here, joint A. And when we look at it, we have this the top chord coming in right here. We're going to call it TAD. And then we have a bottom chord, call them TAC. Then you have the reaction, which we calculated was 3.12 kip. And up here we have 0.66 plus 0.24. That it basically comes out to 0.9. So 0.9 kip on top. One thing is, we learned this in kindergarten again, when you have a force, the force has a direction. This, because it's coming in an angle, has a horizontal component and has a vertical component. And the pitch of it is 6 on 12. Instead of using sine and cosine, we can just use the pitch of itself. So I'm going to say 6 on 12 is the same as this right here. If I got 6 on 12, if I divide this by 6, it becomes 1. And if I divide by 6, it becomes 2. So basically, I can say, oh, wait a minute, that is the pitch of this is basically 1 on 2. It's the same thing. And therefore, this hypotenuse become square root of 5. Remember Pythagorean theorem? 2 square makes it 4, plus 1 square makes it 1, become 5, square root of 5. And that's, we have that. And that comes in handy when we figure these things out. So I can go ahead and make a little direction arrow, like I said, okay, that's 1, 2, square root of 5. So let's go ahead and figure this out. If I do summation f of y, I can solve that, not a problem. So I'm going to say this, and just give you background on trusses. Each joint is rigid. That means summation all the forces in horizontal direction, in the vertical direction, it becomes 0. If it doesn't become 0, then you're in trouble, because that means things is collapsing. So summation f of y is equal 0. Going up is positive. I have a 3.12 minus 0.9, then minus the vertical component of this is going to be 1 divided by square root of 5 times TAD, and that's all I have, is equal 0. Therefore, simple calculation, TAD comes out to be 4.96 kip. Okay, and let's figure this one out. Because we assumed this was in compression and we put the arrow into it, and our number came out positive, that means we are correct. This is in compression. So I'm going to put a C in front of it for in compression. And I assume this one is in tension, that means the arrow goes in and out. So let's go ahead and calculate again. Summation f of x is equal 0. Going to the right is positive. I have this one, TAC, and then I have this one going the other way, minus the horizontal component of that is going to be 2 divided by square root of 5. And we said TAD came out to be 4.96. 4.96 equals 0. Therefore, TAC comes out positive number. That means our assumption was correct. That is in tension. And that comes out to 4.44 kip in tension. Now, when we're going to go ahead and size these members, because this top one is in compression, the bottom one is in tension, so we have to do combination. This one is going to take bending plus tension. This one is going to take bending plus axial compression. And this one, bottom one, will be axial tension. So let's go ahead and do it. Now we have this number. Let me erase this and we start over again. We're going to go ahead and size the bottom member. The bottom member, you have a piece of a wood from here to here, because there's a joint here, there's a joint here. Then you have to connect it here, and you have to connect it here. So this board is going to be 15 feet long. And that same board, per hour calculation, per hour load, we know it's going to be in tension, because I got to hold the roof back from collapsing. And we said that tension is has to be carried. It's going to be a 4,440 kips tension in it. But also there's a weight of the ceiling on top of this member, so that's going to cause bending. Now we have two problems. We got bending problem and we got axial problem. So now we go ahead and figure this out, see how we're going to size it. One of the things about design is, if you experienced designer, you just go ahead and call it and say, I'm going to use 2x4, 2x6, 2x8, whatever. And then you run it through, see if it's going to work. If it's going to be undersized or oversized, and you come back and refine it. So let's say we're going to say, we're going to try, we're going to use a 2x8. This is a 30 feet long, remember? So, and it's going to be, it's a 4 feet on center. So I'm going to use try 2x8. And then, depending where you're going to buy the wood and what's available, what's a good price. Let's say it's locally available at the lumber yard. I'm going to buy 2x8 number 1 and better. Humfer. So I'm going to go ahead, go to NDS table 4A and find the property of this wood, find out what the strength is. Go ahead, take a look at it on the screen here. Okay, so now we said, going back to NDS table 4A, we're going to find all these FB and FT and CF, and then from table 1B we can find out the cross-sectional area of a 2x8 and a section module, which there comes out this number. And one thing you got to keep in mind is, if you look at this cross-section of this board right here, and which is a 2x8, and that means is 1.5 inches by 7 1/4, 7.25. And then you have this, then we're going to, how are you going to connect these two together? So you're going to put a bolt through it. We're going to put a hole through it and a bolt. What is the size of this hole? If we do, our bolt is going to be 3/4 inch, then the hole got to be at least 1/16 bigger than, per code, 1/16 bigger than bolt diameter. And then we're going to say, what is the net cross section? We're going to deduct the hole from here. So we're going to say the net cross section is equal, let's take the hole out, and that's going to be 1.5 times 7.25. I'm going to take out the size of the hole, which is here, so let's take that out, and minus, we said minus basically the diameter. Let me put another parenthesis here. The diameter of the bolt is 3/4 inch, 0.75, and add another 1/16 to it. 1/16, I don't know what 16 comes out to, 1/16. Then the whole thing and see what it comes out to. That comes out to 9.166 inch square, so that's the net area. Our tension, F at T, that is due to the load. This load, how much stress can I put on this cross section, that is equal. We said that was a 4,440 pound, and the area came out to be 966, and that give me about 460 pound per square inch. So that is how much force, how much stress we have based on the load, based on this load, on that member right here, just for tension. But let's find out what is the capacity of the 2x8 for tension. And that's going to be F at T prime T. This is from 4.31 NDS 4.3.1. That is equal So from NDS 4.31, F prime T is equal F at T times these number. We figured out F at T came out to 725 from a table 4A, which I erased up there. These are adjustment factor. Because timber is special, how do you use timber? You have to adjust it how much weight it's going to take. Like timber, if it's used for a short time, then the strength is, you can use it double. But if you use for a long time, then different story. If it's under wet weather, then it's different story. If it's inside at normal temperature, then it's different story. So these are the adjustment factor, that's what they put in here. Because ours is going to be inside and it's going to be in dry, so most of these are going to be 1, except for CD is based on a load, which comes out to 1.15. Look at other video we have, and we learned that in class. And size factor was 1.2. So now the adjusted value for tension capacity of the beam comes out to 1,000 pound per square inch. And this number is way bigger than 460. So we're going to say, oh, okay. There's no way this is going to fail by tension. It's not going to rip apart because the capacity is 1,000 pound per square inch, yet our load only causes 460. But what about bending? This causes bending. Let's figure that out. The moment caused by this weight of the ceiling is M is equal W L squared divided by 8, and W was 32 pound, time L is 15 feet squared, that divide that by 8, and that comes out 900 foot-pound multiplied by 12, and that makes it to 10,800 inch-pound. Okay, so now we have that, and we're going to say also the same, based on the same thing, our F of B is equal moment divided by suction modules, and that is the stress caused by the load itself. So we have 10,800, divide that by S came out to be, I erased it, 13.14, which is equal 822 psi. So that means the stress caused by that load on the bending is 822 pound per square inch. But what is the capacity of the wood? So the capacity of the wood is F prime B, and that is equal, again from in DS 4.31, it is FB time bunch adjustment factor, which they are CDCM CT. So this adjustment factor, most of these are one because they are inside. CI is not a pressure treated, so it's inside. And also, so the only thing really we have to worry about is this two right here. And that comes out 2. And we found out FB from the table 4A. Okay, go ahead. So from table 4.31, FAB comes out to this. And the CD factor, because this is just a dead load, down here's a dead load and there's no snow load, and that becomes 0.9. Size factor doesn't change. So this comes out to the capacity bending stress for 2 by 8, and under that condition, just carrying dead load comes out to 1,188 pound per square inch, and that is bigger than 822, and we say we are okay. So now this size that we measured 2 by 8 came out to be okay for both bending and for tension. You may be doing this in real life. Says, what about if I use 2 by 6? If you use 2 by 6, go through this. Might work, might not work. I just picked 2 by 8 for this example. You know what to do. So that's this. Let me erase this. I'll continue. I'm just going to go up here. So the member is both in axial tension and bending. And we have two different load cases. One is we just considering dead load, and the other one considering dead load plus snow load. When we did bending, it was just the dead load of the ceiling itself. When we did tension, we had the tension was based on dead load and snow load. But this one, the factor is 0.9. The other one is the factor is 1.5. So what happened if we use 1.5? So let's call it F star B, and that's FB time all those factor. I'm not going to write it down, so it's going to be 1100 time, instead of 0.9 we did previously, which I erased, I'm going to use a 0.15 and multiply by other factors, and I think there was 1.2 and a bunch of ones, and this comes out to be 1518 pound per square inch. I erased it, I shouldn't have. And so if we use the equation here, which I put on a board right there, the for a combined stress, if I have a F at T, divide that by F prime T plus F of Bx divided by F star B, what we get for ratio. We figured this out to be was 408, if you remember, and F prime T came out to be 1,000, and that is a plus. This came out to be 822 if you look at the number, and this one we just did it was 1518, and that will give us about a 95%. So that means the member is 5% over designed. The 2 by 8 is okay. Okay, now we did this. We're going to go ahead and design the top chord, which is in both compression and tension. I'll go ahead and look at this member right here, AD. And AD is about from here to here 7.5 feet. And from here to here 7.5, so that is 7.5 divided by 2 is 3.75. The pitch is 6 on 12. I'd like to know what the length of this is first. So it's basically, you know, in right triangle, this is what? If this is a this is a B, this can become out square root of A squared plus B squared. Remember, look up in the book, you can find that out. So I'm going to say this L going to come out to equal square root of 7.5 squared plus 3.75 squared, and that comes out to 838. This piece of board here, 2 by 8, is write this 2 by 8. At the top, there's a plywood. That piece of plywood on top of it, because you got every 4 feet, you got the 2 by 8 top chord of the truss, and the plywood is on top of it. So keep that in mind. If you're looking at this member here, because this roof truss, it repeats every 4 feet, and there's a plywood on top of it. And we're going to come and look at the cross section of it. It's going to be plywood on top of it. Because we use 2x8 down here, we really should use 2x8 over here, see if it works out. Well, one thing we're going to do here, before you look at this, let's go ahead and just change the material. Say in here we use hemper. Here this is a southern pine. Use southern pine. And if you go to table 4B, southern pine, looking on the screen, for 2x8, which is 8 inch wide, your compression force is 1,600 pounds per square inch, and your bending is 1,350 pounds per square inch. In the table, we're going to find out the, I'm going to write it here, E minimum. E minimum comes out to 660,000 psi. And table 4B, we can also find out CF comes out to 1 for all of them. And going back to the same cross-sectional area that we had before for 2x8 from table 1B, we said area is 10.875, and section module was 13.14 inch by power 4. Let me write that down. I can do better than that. There. So now you look at the column, the joints right here and the joints right there. There's the joints, but we worry about the buckling between right here. And always the buckling happened from away from the joint. If we remember when we did column design, and how the both ends are supported makes a big difference. And here we just say it's a pin. So our unsupported length is going to be 8.36. And the compression force, this number is in compression, and we said it came out to be 4.96. And that is FSC is equal P divided by A. The A is not a net area, it's going to be the gross cross-sectional area because it's from here to here. And our P was 4,960 or 4.96 kip. This should be a kip right here. And divide that by the area at 10.875 equal 456 pounds per square inch. Now we're going to go ahead and calculate the capacity of the member itself based on the species. This was this is the applied load stress. And to do that, we would just go back like what we did with the column, and we said our unbraced length in this is 8.38. One thing we're going to know that LE and divided by dy in y direction is equal 0 because you have the plywood on top. It will not allow buckling. But in the other direction, it will be LE divided by d. In x direction, it comes out to be 8.38. Multiply that by 12 and divided by dx, which is, and divided by dx, which is basically 7.25. And this dimension right here, from here to here, is 7.25 because it's a 2x8. The dress size is 7.25 by 1.5. So this comes out to 13.9. And at the same time, our E prime minimum is equal E times CMCT, which these two are 1 anyway. So basically, you're going to come out to 660,000 times 1, 1. So it's 660,000 psi. We're going to go ahead and calculate the capacity of the column based on what itself what we have. And if we look at the NDS section 3.71, first we're going to go ahead and calculate the column stability factor, CP. To do that, we have to do a lot of things. And one of the things is from that, we know C is equal 0.8 for sawn lumber. And that equation is a long equation. Before we go to the equation itself, let's calculate some of the component inside of that equation. And that is critical buckling FSCE, which is equal 0.822 times E prime minimum, and divide that by LE divided by D square, which is equal, in our case, comes out 0.822 times 660,000, and divide that by 13.9 square. So that comes out to 2816 psi. Then we're going to go ahead and calculate the F star C. That's the same as a F prime C minus the CP. So if you look at the from NDS 4.3.1, we can figure that out. Okay, so from table 4.31, F star C is equal this, but they have F prime C time CP. And we take CP out, basically saying F prime C is equal F star C times CP. You can figure that out yourself. So that's why I'm just interested in F star C. Later on when we find CP and we calculate this F prime C, that we need that. But before, I want to know what this is, because I don't know this value. We got to work on this. So this comes out to be 1600. That's CD came out 1.15 just like before. And I think rest of them is 1, and there's no size factor for this one here. So that comes out to 1840 psi. So FSC divided by F star C is equal to 2816 divided by 1840, and that comes out to 1.531. And also I need to find out what is, I tell you why I need this, 1 plus FSCE divided by F star C. That comes out to 1 plus 1.531, and this whole thing actually divided by 2C, and C is 0.8. So divided by 2 times 0.8, and that comes out to 1.582. Why do I need that? Because I have to calculate CP. Let me write this formula down. And CP is equal So the whole idea is here, we're going through all this here to calculate the column stability factor. Why do I need column stability factor? Because F prime C from table 4.31 is equal FSC time all this stuff plus multiply CP. But I don't know CP. In order to calculate CP, I need to know what is the critical buckling is, FSCE, which we calculated. And then I need to know what the F star C is, which we calculated right here. Came out to be that. And then we're going to go ahead and use the column stability factor, this equation. That's why I did all this stuff, so I can plug the number, be a lot easier rather than putting all this stuff in. So that's going to become equal C. This came out to be 1.582 minus square root of, and 1.582 square, and then minus, run out of room, see if I can make it work, 1.531 divided by 0.8, and my CP comes out to, you can plug it in yourself and double check me, 0.815. All this for here. So now I can calculate my FSC up here. I'm going to do it in a different color. So that's going to come out to, first RC came out 1840. 1840 time 0.815. And that comes out to 1499. And that 1499 is more than this one here, so it's more than 456 psi. I mean, is okay. I'm running out of room. Let me erase this here. And we calculated this based on from here to here. Remember that. So there's no, we didn't calculate at the joint when the cross section has a hole in it. So we calculated before the hole based on this equation, but let's go ahead and use that one too. I'm going to go ahead and erase this section here so we can do that. Okay, so we did calculate AN. I don't know what it was, came out. We erased it from beginning, but I think AN came out. I don't have it. Let's do it again anyway. AN is equal, if we put a hole in here, right at this point, it's going to be 1.5 time and 7.25. 7.25 minus the hole, and the hole itself is 3/4 inch bolt, 3/4 inch bolt plus 1/16, make it larger for size of the hole, and that came out to be 966 inch square. Then we're going to go ahead and say the compression, just like we did here, we're going to divide by AN is equal P divided by AN, and that is equal to 4,960 divided by 9.66, and that comes out to 514 psi, which way still less than, I want you to remember something here. We calculated this to become 1499, right? And however, that is for from here to here because we have to use a stability factor because there's a buckling issue. But right here at the joint, there's no the stability factor is no, it's 1, so you don't have to worry about that. So our F prime C is going to be different. Our F prime C is going to equal FSC time CD CM CTCI, CTCI, CF, all that stuff, which is basically they all come out to be 1840, right there, 1840 psi, and that is more than 514. We okay at the joint also. So now we got to worry about this is also act as a beam because there's a weight on top of it. Let's do check for bending. We did check for compression, check for bending. Let me erase this. Check for bending, and we know the bending equation, just like we did previously, is the moment is equal WL squared divided by 8 for uniformly distributed load, simply supported, and that came out to 176 time 7.5. Remember that's distance is 7.5 square divided by 8, and that comes out to 14,850 inch pound. And we know the bending equation, F of B, is equal M divided by S, which is equal 14,850, and S was 1314, and that's equal 1,130 pound per square inch. So from table 4.31 again, F of prime B is equal there. F of B came out to be from table 4B, 1350 time 1115, and the rest of them are a bunch of ones anyway, and that came out to be 1553, which is more than we just figured out 1130, so we okay right there. Okay, the one last thing we want to check is a combined stress, because this member both is in compression and also bending. So this is a combined stress. This should come out less than 1. And we already have calculated all this stuff. FSC came out to be I erased it. It was 456. And then we had this one came out to 1499, if you remember, plus, and 1 divided by 1 minus 456, divide that by, came out to 2816, and multiply by FBX, I think we just have it right here, 1130, and divide that by 1553, and that comes out to 0.96, which is less than 1. We are okay by 4%. So this is how it's done, and I hope you enjoyed it. If you liked it, give it a thumbs up. Have a good day.